In this video, we're going to derive the kinematics equations. Now, the kinematics equations are based on the idea that the acceleration of an object is constant. Meaning, if we know that the average acceleration of an object is really just the total change in its velocity divided by the total change in time, well, the average acceleration is really just the acceleration itself, because the acceleration is constant, then the average acceleration has to be the same as the actual acceleration, right? So this is still going to be delta v over delta t, right? So delta v is just the change in velocity, so we could say it's the final velocity minus the initial velocity, right, divided by the change in time. And when we're thinking about the change in time, right, usually we associate change in time with the final time minus an initial time of 0. And so really, we like to think of delta t just as t, right? And so that's the case when it comes to the kinematics equation. So we're just going to write t for that. Right, next what we're going to do is we're going to multiply t on both sides of the equation. Right, so notice how when we do that, t will actually cancel out right here and right here. And so what we're left with is at equals v minus v sub 0. Right, and flipping these equations around, we'll get v minus v sub 0 equals at. Adding v sub 0 to both sides, we get v equals v sub 0 plus at. And so this right here is just one of those kinematic equations, right? V equals v sub 0 plus at. All right. The next one is pretty much, there's another one that's based on the idea of average velocity under a constant acceleration. And we know that average velocity under a constant acceleration, that is just going to be pretty much the initial velocity plus the final velocity divided by 2, right? Now, this is basically the average velocity of an object undergoing constant acceleration, right? Which is what the kinematics equations are based off of. And we know that average velocity, we know that's just the displacement divided by the change in time, right? That is average velocity. And remember, delta t we like to write just as t, right? So we're going to write delta t as t. So this is equal to v sub 0 plus v over 2. So next we're just going to multiply t on both sides of the equation. And so what's going to happen is t will actually cancel out here, right? And so we get that delta r, right? So what this really is just going to be 1/2 t times v sub 0 plus v. And so this is another kinematics equation, right? And so yeah, as you can see, we now have two kinematics equations. So next what we're actually going to do is we're actually going to combine both of these kinematics equations. Check this out. If v is equal to v sub 0 plus at, then why don't we just substitute this into here? That would give us another equation, so let's just do that. So really, using this equation, we know this is just delta r equals 1/2 t times v sub 0 plus, and we're going to replace v with what we have right here, right? V sub 0 plus at. Right, and now we're just going to simplify this, okay? Right, so inside of parentheses, right, v sub 0 plus v sub 0 is really just 2v sub 0. We're adding at, right? And now we're going to distribute the 1/2 t through this parentheses. And so we get that delta r is equal to, right? And so distributing the 1/2 t, we're going to get v sub 0 t plus 1/2 at squared. And so as you can see, we get another kinematics equation. And so yeah, we now have 3 out of the 4 kinematics equations. And so pretty much there's one more. So how do we derive the other one? And where do we go from here? Well, notice how all of these kinematics equations, they all contain time in it. They all contain time, right? Time here, and we have time here, right? Well, the other kinematics equation we know doesn't contain time. So what if we were to make sure that our next kinematics equation that we find doesn't contain time? Right? It turns out what we can do is we can solve for time in this kinematics equation, right? So I'm just going to go over here. we're going to rewrite this kinematics equation up at the top right here. Right, so v equals v sub 0 plus at. Right, we're just going to solve for t. If we were to solve for t, we would get v minus v sub 0 over a. Right, this is what we get if we solve for t. What if we just substitute t, right, we substitute this in for time in this equation? We would get a kinematics equation that doesn't contain time in it. Right, so basically, I'm just going to rewrite this equation, by the way. I'm just going to rewrite it right here. So delta r equals 1/2 t times v sub 0 plus v. Basically what we're going to do is, I'm going to just show you, is we're going to substitute this, or we're going to substitute that in for time. That's basically all we have to do, and we're going to get a kinematics equation that doesn't contain time in it, right? That's the whole idea. So delta r is equal to 1/2 times this, which is just v minus v sub 0 over a, right, multiplied by v sub 0 plus v, and this we just got to simplify it. And notice how we could actually rearrange this into saying 1 over 2a, right, pretty much just moving the a with the denominator, and then we have v minus v sub 0 times v sub 0 plus v, right? We can agree that this is equivalent to this. So now that we have this, basically, I'm actually going to rewrite it right here just because you probably can't see it. Might be a blind spot right there, but I'm just going to rewrite it. Right? But the idea is, check this out. We know that v sub 0 plus v, we could just use the commutative property and switch these around, right? Right, and so in that case, we could say it's the same thing as v plus v sub 0. And so notice how this is really just a difference of perfect squares when we multiply these out. And so what we really get is we get v minus v sub 0, except both of these are squared, right? That's when you multiply these out. It's just a difference of perfect squares. All right, and next, all we got to do now is we have to multiply 2a on both sides of the equation. And so you can notice right here, yet again, we get some things canceling out when we do that. 2a cancels out. And so what we're left with is 2a delta r equals v squared minus v sub 0 squared. Right, basically just rearranging this, pretty easy to rearrange this. We could say that v squared is equal to v sub 0 squared plus 2a delta r. And so as you can see, we have now derived the fourth kinematic equation. And it doesn't contain time in it, and we know about this one. So as you can see, these are pretty much the 4 kinematics equations, and we derive them using algebra, which of course we can do, right? The acceleration is constant. And so this is one of them, this is another one, this is another one, and here's our other one. And so this is pretty much the whole idea of the kinematics equations. And so that's pretty much it.